So I decided I would share with you a little project I've been working on. And for this project, I'm going to be using the Raspberry Pi Pico. It's a dual-core ARM Cortex-M0 processor. By default, it runs at 125 megahertz, so that's what I have it running at. There's 264K of RAM on board, and which I'm using more than half of. And one of the coolest things about it is these programmable I/O state machines, which I'll get into. It allows a tremendous control over how you interface this microcontroller with external devices. Okay, so what we're going to do with this is we're going to drive a VGA monitor. So here we have a monitor right here. It's actually an LCD, but it has a VGA input. Unfortunately, I can't get it to do a 4:3 aspect ratio, so it'll stretch things out, but that's okay. And here we have the main Raspberry Pi Pico that is being used to drive the monitor. So here's the microprocessor. We have a resistor network for converting digital signals for RGB values into analog signals that can be understood by the monitor. We have sync signals that are also being sent to the monitor. And here we have another Raspberry Pi Pico configured as a Pico probe for debugging and reprogramming. And then here we have a VGA cable. So what we're going to do is we're going to turn this on. And here we've got a nice little test pattern. And so this shows you the 16 colors that are available. And I'm going to run a couple of test programs to show you what it can do. So one of them is just going to show you some simple, like here's some text. We got bold, and it can, since it's all graphics, we can support underlined and a couple of different background colors. And then I thought I would do something funky like dump a big text file to. I have a VT102 terminal emulator that I wrote like back in '99 that I managed to find on SourceForge still. So I went ahead and snagged that and re-uploaded it to GitHub. And that's being used to do this terminal emulation. So basically, I'm dumping data to the serial port, which at the moment, the Raspberry Pi thinks of as its console, like its input and output console. So it's basically doing get char on the console and then sending it to the terminal emulator. So, and as you saw before, we can do VT102 with different colors and that kind of stuff. Another thing that I did was I added some little ad hoc graphics thing to the terminal emulator that supports graphics. So just to give a little background here, one of the things that I wanted to try to do was actually like have a text buffer, 80 by 30 actually for the 640 by 480 resolution here, and then translate the text on the fly into pixels into a transmit buffer that would then get sent to the monitor. But it turns out there's absolutely no way that I can do that fast enough. The pixel clock is 25 megahertz. The CPU runs at 125 megahertz. So that's 5 cycles on the CPU per pixel. And there's not a whole lot I can do in that time. So basically I have a full-on graphics frame buffer, which takes up more than half the available RAM on this device. But what that does is it gives us arbitrary graphics. So I wrote another test program that uses a feature I added to the terminal emulator to display graphics. So here we go. I used GIMP to dither this toucan image to the available 16 colors, and then I'm just sort of transmitting that over to the Raspberry Pi through the terminal emulator. So here we have a basic drawing of the important signals involved in driving the VGA monitor. So some of the GPIO pins have been reserved to as control signals for the monitor. So we have we have a resistor network to generate red, green, and blue. 4 of the GPIOs control the color. These are where the signals will be connected to the VGA cable. We have horizontal and vertical sync. So I'll show you here what it is we need to generate in order to control this monitor. So what we need to do is generate analog signals for video, red, green, and blue, and some digital signals for to control the timing. So what we want to do is we want to output 640 pixels to the monitor, and then we have a horizontal blank period where we have 16 pixel clocks of what we call the horizontal front porch, and then we have a sync signal that is 96 pixel clocks and a horizontal back porch. And so the monitor is looking for these signals to try to figure out what is the timing of a scan line. And then for the vertical period, we have our 480 scan lines, and then we have 11 scan lines of blank, that is the vertical front porch, and then we assert the vertical sync signal for 2 scan lines, and then the remainder of the vertical blank period is 31 scan lines. So to generate the colors, we have a little resistor network here that I devised for this, and I'm going to we'll show you how this works. So we have the GPIOs that control the colors. We have the red, green, and blue. We have another signal that like brightens the pixels a bit. And so we have this arrangement of resistors, 470 ohms connected to these GPIOs, and 680 ohms connected to this one. And so for each of the for the red, green, and blue signals, there are 4 relevant states that these signals can be in that specify what signal level is going out to the monitor. So we have the 2 resistors in the resistor network and a 75 ohm resistor inside the monitor that is generally used as a termination resistor to compensate for the fact that the VGA cable has a 75 ohms impedance. So one state is where the GPIOs are pulled down, and so everything's pulled to ground, and so we get 0 volts, and we'll call that 0% brightness. Another state is where both of the GPIOs, say this red one and this lateness one, are both pulled up, and so the harmonic mean of these 2 resistor values is about 278 ohms, and the voltage divider we get gives us about 21%. You multiply that by the 3.3 volts, and that gives us the 0.7 volts, which the VGA monitor interprets as fully on for that color channel. Another state that we can have is where the smaller resistor is pulled up, the larger resistor is pulled down, and so now we have this resistor network where the harmonic mean of these 2 resistors is 67.5 ohms, and then we end up with a voltage divider that gives us about 12.5% times 3.3 volts. Gives us a 0.415 volts, which is about 59% of the maximum brightness, and then the last state is where the larger resistor is pulled up and the smaller resistor is pulled down. So we have the harmonic mean of these 2 resistors is about 64.6 ohms, and then we end up with a voltage divider, which gives us about 8.5% of 3.3 volts, or 2.866 volts, which is about 41%. So we can get, for red, green, and blue, we can get full brightness, we can get about 60%, we can get about 40%. So the color, because we share a single GPIO signal for this lateness signal, that means there's only 16 colors because you only got 4 outputs. And so these are actually the colors you get. So here we get 60% levels on red, green, yellow, blue, magenta, cyan, and light gray. And then if you pull up the lightness signal, it increases everything by this additional 40%. And so it just adds that to these those 8 colors to get these lighter ones. So the Raspberry Pi Pico has this brilliant little feature that they call PIO, programmable I/O, and it is basically a programmable set of programmable state machines for controlling and interfacing with external I/Os in really sophisticated ways. So you can do if you think of it, you can probably do it. Driving ring LEDs with weird encodings, doing UARTs, doing SPI and an I2C, and it's really quite impressive how this works, and it's all done with this limited set of instructions. So let's go over how I'm using the PIO state machine, one of them, to drive the VGA monitor. So this is the sort of assembly language program that generates a single horizontal scan line that is sent to the monitor. Okay, so at the beginning, we start with the vertical blanking period. So the first thing we do is we assert an IRQ so that the CPU can set up a DMA transfer. That is what's going to transfer data from memory to the state machine, which is then going to send it to the monitor. Then we have our horizontal front porch and the horizontal sync period. So here we assert the horizontal sync, then we wait, and then we deassert the horizontal sync. Now these timing numbers are all hard-coded. I tried a variety of different approaches before I just decided to give up and hard code them, but what I can probably do is write code that will programmatically generate new state machines for different timing numbers. Okay, and then after the horizontal sync signal, we have the horizontal back porch, and then finally have the horizontal active period. What I've done is load the number of pixels I have to scan out into the Y scratch register, which I then copy into X and then loop that many times. And so the pixel clock is 25 megahertz, but because this loop has to go has to have 2 instructions in it, I have to run the state machine at 50. Okay, so let's see how we set this up. So we have for out instructions and set instructions that set pins, we can set different pins. So basically what we're doing is we're saying that these GPIO pins on the microcontroller are being controlled by these instructions of the state machine. So for out instructions, we're going to set up 4 pins for the red, green, and blue, and lightness signal. And then for set instructions, we're going to set up the horizontal sync pin. We're going to do the data is being sent by DMA to the PIO 8 bits at a time, where we shift right, so it's a little endian, and also this out instruction is going to pull data from the queue automatically. There's this auto pull feature that's enabled. This sets up the GPIO directions and connects them to the PIO, otherwise they'd be controlled by the CPU. So now we can do all of the horizontal timing numbers for the horizontal blanking period. We can hard code the numbers in the state machine because there's a 5-bit immediate value that's available for set instruction. But for the active period, we need a much larger number. We need 641. Okay, so the only way to get that is to set it up some other way. So what I'm doing here is I'm pushing this number, 641, which is going to tell it to do 642 iterations of this final loop. I'm pushing it into the transmit queue of the state machine. And then I'm forcing the state machine, even though it's currently stopped, to execute a pull instruction and then an instruction to copy the value that it pulled into the Y scratch register. So that then when we start this loop, I can copy from Y to X and loop the number that's in the X register. And then we start that up. I've also provided a function for connecting the IRQ to the interrupt service routine for the horizontal blink period. And then I have a routine that's called one time at startup to configure the DMA channel that's used to transfer the pixel data to the state machine. And then at the beginning of every scan line, at the beginning of the horizontal blinking period, I call this in order to initiate the DMA transfer. Okay, so now that we've covered what goes on in the PIO for controlling the I/O signals, let's go over what's going to run on the main CPU. Now, one of the things I'm not going to go into is this G-term. You can find it at my GitHub page under TheoSib. If I remember, I'll link it in the description. But basically, this is an abstract VT102 terminal emulator that, as I mentioned, I wrote in '99. And I've actually fixed a few bugs in it just now. But anyway, I'm using that to take whatever is the text going to the display and convert that into graphics. So the G term doesn't care what its output device is. The sample that I provided with it back then was for X11. And here I just wrote a new implementation that calls out to render the text to the VGA display. So here we have the timing numbers that I mentioned before. I'm going to be using a DMA channel to send data to the PIO. I've selected which GPIO pins. Two of them, 0 and 1, are being used by the Pico probe, so I have to start at 2. For drawing text, I went ahead and pre-computed a mask. So basically, we have 8 by 16 characters in our character set, but they're 4 bits per pixel. So 8 times 4 is 32. So we get a 32-bit word is the breadth of a character. So this thing just expands out these 8 bits into these 32, which then we can mask with the colors in order to display, in order to plot part of character foreground and background color. Okay, so in order to fit all of this in memory, we need a huge frame buffer. So it's this many bytes, whatever that number is. There's an extra scan line because we need a blank one during the vertical blinking period. Now, I play an interesting trick here. What I do is I bust out pointers to each scan line. So this way, when there are certain circumstances under which scrolling can be done not by copying data in the frame buffer, but just by reordering the order in which scan lines are sent to the monitor. So I'll show you some of the code for that. So here's I'm not using this routine anymore, but basically, if you give it a start and end region and the extent by which to scroll it, and this just reorders the lines, so that basically there's 0 copy to scroll a region in the display. So for drawing a single character, as I mentioned, they end up being 32 bits wide because 8 times 4 is 32. So I break out my foreground and background colors, replicate them across the 32-bit word. Okay, so now I'm getting the row in memory. So since the scan lines are reordered, I have to look up. I want row 37. Okay, where is it really? Which row is it really? So that looks that up. I add the X offset in 32-bit units. Now here I have my display font. So I get the first byte, first row of the character. So I grab a row of the character, I expand it out to the mask, I mix the foreground and background colors and store it in memory, and voila, we had, iterate 16 times, we have drawn a character. For so for the terminal, what I've done is I override these methods for the gterm class in a child class, and so I call out to these functions to do various rendering operations, like drawing a string, drawing a line for underline. We can scroll regions of the display by doing by copying pixels around on the screen. We can clear parts of the display. So these are callbacks from the terminal emulator, and then we have code in the implementation here that does this. So this renders an entire string. These are some. Okay, we got some memory copy and set routines because these are faster than the ones that are built into the ROM. This plots a pixel for the toucan I just showed you. This clears so many characters wide for a selected line. This draws like a single pixel tall horizontal line that's used for doing an underline. And then this is the copy area. Okay, so here's a generic implementation. Like I've got a region on the screen. I want to copy some width and height of pixels from some source location to some destination location, and this will do that, and that's for the sort of the general case. But if it just so happens that the width is the full width of the display, and these are kind of sanity checks that the source and destination x coordinates are all the way to the left. Okay, so basically what we want to do is do a vertical copy of scan lines that are the full width of the display. Now we can use that line renumbering feature. So if they're not overlapping, we'll just swap the source and destination, and if they're overlapping, then I have different basically I'm copying pointers around in order to renumber the scan lines. Okay, so now you'll recall that at the beginning of this routine here, this PIO state machine, that there is an interrupt service routine. Well, an IRQ is asserted. Okay, so here we have the interrupt service routine. By the way, this is important for performance. Okay, so we're keeping track of the scan line we're on, and so if we're in the active period, we're going to set up a DMA for the current scan line. As I mentioned before, we need 321 bytes because the last 2 pixels need to be black. And then if we're in the vertical blanking period, here we're manually, I guess you could say, controlling the vertical sync signal. So basically calculate if we're in that vertical sync period. So we have a vertical front porch, then we have a vertical sync signal for 2 scan lines, and then we have a vertical back porch. So if we're in the sync signal period, we're asserting the signal, and then we're also sending out a blank scan line. Okay, so you increment the scan line, and then we clear the interrupt. So we have a little bit of setup here. This basically loads the PIO, and this configures it. Here's our 50 megahertz clock, and it's easier, by the way, to control the sync signals are active low, so we want them to be high, digital high, 3.3 volts, and then when they're being activated, we want to pull that signal low. And so it's the easiest way to handle that is to set the GPIO to 0 for unasserted high, and then when we set it to 1, it actually comes out of the pin as a 0. So we're basically inverting the sense of these signals. Here I'm setting up the interrupt service routine for the IRQ, and then configuring the VSync output. Okay, so now let's go down to main. I've done all the setup. This is that funky test pattern that I showed you. This can go, and so we're gonna do a little bit of basic setup, and we're gonna do most of the work. The terminal emulator and the ISR are being handled on the second core. What's really nice about this is that we have a dual core system. So basically, what this main routine does is it just gets a character from the input and puts it in a queue, which is then, so the UART, by the way, only has a handful of characters. So if the terminal emulator were to fall behind on computing what to do, like you had to do a bunch of work for drawing characters or something, that you could lose characters. So what I'm doing is on the CPU 0, I'm pushing characters into a FIFO, and so we can definitely keep up. So we push them into this 4K ring buffer, and then here for core 1, so the second CPU core, this is where we do that setup of the PIO. And we're doing it here so the IRQs get routed to this CPU core instead of the other one. We're setting up our terminal emulator, and then here we're just getting characters out of the ring buffer and sending them to the terminal emulator to be processed. And then I've set up this sort of timing situation so that it only actually really tries to update the display 60 times a second. You do it faster, it's kind of wasted effort, and also it makes the cursor look really weird as it gets kind of split. So anyway, so yeah,